learn our first derivative formulas. And this should be relatively quick. So we're going to work through the demo part. You'll do the group activities. And then I'm going to see where we are. And if we have time, I'm going to do a little bit of, give you a little bit of guidance on the arbitrating disputes project. Okay. All right. So some notation. We're going to see this notation formally in a few classes, but generally, when I write d dx of something in square brackets, means the derivative of what's in the brackets. Okay? So d dx means the derivative of. So if c is a constant, then d dx of c is 0. Right? So let's think about this. If we wanted to think about it graphically about the slope of a tangent line, if I had a function that's a constant, right? What's the slope of the tangent line at any point there? 0. Yep. Draw a tangent line anywhere, and the tangent line is going to be the line itself, and it's going to have 0 slope because it's horizontal. Okay, so the derivative of any constant is 0. So what is the derivative of -7? 0. Good. Okay, so now we're onto the power rule. We've seen a little preview of the power rule in a couple of different places. It says that if you want to take the derivative of x to the n, x is the variable, n is a number. Only works when the variable is the base and you have a number as the exponent. It says you take the exponent, bring it down in front of the x, copy the x, and then you reduce the exponent by 1. Subtract 1 from the exponent. Sure. We're going to get there. Yeah. What do you do if there are other terms in the brackets? That's one of the rules we're going to see today. Okay, so if I want to find d dx of x to the 6th, copy down, bring the 6 down in front of the x, copy the x, subtract 1 from the power, so 6 minus 1 is 5. And we saw a little preview of this when we were drawing derivatives last class. We started with something that looked like a 4th degree polynomial. We sketched its derivative, and it looked like a 3rd degree polynomial. So the power rule says that is, in fact, true. Okay. That is the slope of the tangent line at any point on x to the 6th. Okay, how about d dx of x to the -4? Bring that -4 down in front, copy the x, subtract 1 from the power. What's -4 minus 1? -5. Good. Ooh, here's a trickier one. I have the cube root of x to the 5th. So first, I probably want to just write that, not taking the derivative yet. I just want to translate that to just a rational exponent. 5/3. Yeah. The root is actually the bottom of a rational exponent. Keep your roots in the cellar. Yeah. So this is x to the 5/3. So I haven't taken the derivative yet. All I did was rewrite the cube root of x to the 5th as x to the 5/3. So now when I take the derivative, you bring the exponent down in front, copy down the x, subtract 1 from 5/3, and what do you get? 2/3. And that's the answer. Doesn't matter to me. You could put it back in a cube root or not. Yeah. Can we take a derivative? We can, and we're going to do that in a couple of classes. Yeah. Derivative of the derivative, yeah. Okay, so next rule. If c is a constant, and you want to take the derivative of c times some function, you can just pull the c outside of the derivative and multiply it after. Okay. So if we have a special case, d dx of c times x is always c. So let me just do this one with a quick graphical approach. Cx is a line going through the origin. What's the slope of that line? C. So at any given point, if I draw a tangent line, it is the line itself. So its slope is going to be c. So the derivative of cx is always just c, the slope of the line. Okay, so The derivative of a constant times x is a constant. Constant multiples come outside the derivative and get multiplied after you take the derivative. So if I want to do d dx of negative 2x to the fifth, in short, I can just bring the negative 2 along for the ride, right? So this is just going to be negative 2 times d dx of x to the fifth. So the negative 2 can just come right through the derivative. And then what's the derivative of x to the fifth? 5x to the fourth. So this becomes negative 2 times 5x to the fourth. And then you can multiply the negative 2 and the 5, and you get negative 10x to the fourth. After you've done this, like for some people 2 or 3 times, for other people 20 or 30 times, you'll start to realize that when I bring this 5 down, I could just immediately multiply by the negative 2. Right? So you bring the 5 down, multiply it by whatever the coefficient is to get your new coefficient, then finish your derivative rule. Copy the x, subtract 1 from the exponent. Okay. What is d dx of negative 24x? Negative 24. This is a special case. We should be able to do it quickly because it's just a line. But just to drive home the point of the bringing the constant through the derivative, I'll write it out this time. So that's negative 4 times the derivative of x, negative 24 times the derivative of x. And what's the derivative of 1x? 1, so I get negative 24. You don't have to write that out every time. You can just write negative 24. Just really trying to show you that the constant just comes along. All right, so for any constant c, let's figure out what the derivative of c over x is. So I want to take d dx of c over x. And I want to use the power rule because it's the only rule we know so far. So I need to rewrite c over x as c times x to a power, negative 1. Yep. You can move that x up to the numerator as long as you make the exponent on that x negative. Okay, so now I use the power rule. Bring the negative 1 down in front and multiply it by the c. Right? So you're going to get negative c. Copy the x. Subtract 1 from the exponent and you get negative 2. So then this becomes negative c over x squared. Does not matter. Nope. Either of these would be fine. So what is the derivative of 3 over x? Negative 3 over x squared. What's the derivative of negative 5 over t? 5 over t squared. And if you forget this special formula for c over x, you can always rederive it or rewrite 3 over x as 3x to the negative 1 and use the power rule. You don't have to memorize that particular formula. Okay, if you want to take a sum or a difference, Alex, you can take the derivative of each item separately. You want to know what is d dx of f plus g? Take d dx of f plus d dx of g. Derivative of f plus the derivative of g. Yep. For it's a composite function, we have a different rule, and we will learn that in a couple of weeks. That's the chain rule. Yeah. And this same rule applies for addition and subtraction. If you want to take the derivative of a sum, take the sum of the derivatives. Derivative of a difference, take the difference of the derivatives. But it does not apply to multiplication and division. We have a special rule for that we'll learn. Yeah, so it's like distributing the derivative to each term. Yeah. Okay, so let's find the derivative of f of x, which is negative 5x to the fourth plus 7x squared minus 3x plus 2 cubed. Then we're going to find the equation of a tangent line, but we'll leave that alone for now. First, I just want to find the derivative. f prime of x. All right, so because of this rule about sums and differences, I can just take the derivative of this thing term by term. I can take the derivative of each term and just write it down. So what's the derivative of negative 5x to the fourth? Negative 20x cubed. Yeah, you take that 4 in the exponent, you bring it down, and you multiply it by whatever coefficient's already there. So you have a negative 5 times 4 makes negative 20. You copy the x down, and you subtract 1 from the exponent. Then you do that for each term. So what would the derivative of 7x squared be? 14x. What's the derivative of negative 3x? Negative 3. What is the derivative of 2 cubed?
0.
No, I didn't catch anybody. 2 cubed is just 8, right? The derivative of any constant is 0. So that is plus 0. I won't even write it down. So yeah, I was trying to trick you into trying to do the power rule, but that only applies when you have a variable. Okay, so this, anything without a variable, when you take its derivative, it becomes 0. So Eli, you're always reinforcing this for me. What does f prime of x represent? You do.
Okay, that's what
The slope of the tangent line at any given value of x. So if I would like to know the slope of the tangent line at 10, I would just plug a 10 in there, and I would know the slope of the tangent line to f at 10. Okay, the next part of my, that's okay. So the next part of my question is to find the equation of the tangent line. So not just the slope, but the equation of the line, like y equals mx plus b, the whole equation of the line tangent to f at x equals 2. So we're looking for the equation of a line. So the equation of a line, you're probably most familiar with that form. If you learned another form, if you tend to use point slope form, totally fine. Use whatever form you like. Okay. This I just has found is the most common one that people have learned, so that's what I'm going to use for now. So there's the equation of a line. That's what they asked me for. They want the equation of a specific line. And they actually want the equation of the line that's tangent to the function f at x equals 2. So to find the equation of this line, I need a slope and I need a y-intercept. How can I find the slope of this line? Plug in 2 into the derivative, because the derivative tells you the slope of the tangent line at any given x value. So m, the slope of my line, is f prime of 2. The derivative at 2 is the slope of the tangent line at 2. So plug in a 2 here. So 2 cubed is 8 times negative 20 is negative 160. 14 times 2 is 28 minus 3. I don't think I can do this in my head. Negative 160 plus 28 minus 3. Negative 135. Okay, so now I come back to the equation of the line. I say, okay, now I know the slope. Y equals negative 135x plus b, the y-intercept of the line. All right, so what else? How do I find the y-intercept in general? If this was like several semesters ago and I wanted you to find an equation of a line, what kind of information do you need? I need a point, yeah. 2 points, usually at least 2 points, right? Because you need the 2 points to find the slope, and then you take one of them and you plug it in to find the b. How can I come up with a point that's on this line? Plug x equals 2 into f of x. Yeah, because this line and this function f share exactly 1 point. That's what it means to be tangent, right? They touch at exactly one place. So they have this point, 2 comma f of 2, in common. So let me actually just draw a picture of it. So whatever f of x looks like, right? Here's, we'll say this is 2. What I'm looking for is the equation of this line, the line tangent to f at 2. I know its slope by finding the derivative. So now this point right here, the point of tangency, that point is on the curve F. It's also on the line, right? Because it's tangent at that point. So this point here, 2 comma f of 2, we can find the y value because we know it's on the curve, but it's also on the line, so we can use it to get the y-intercept. Okay, so a point would be 2 comma f of 2. So that's 2 comma, I'll just do this all on my calculator. -5 times 2 to the 4th plus 7 times 2 squared minus 3 times 2 plus 8. -50. So that's a point on the curve and on the line. Okay, so how do you use that point to get the y-intercept? Plug it in, the x-coordinate for x, the y-coordinate for y, solve for the y-intercept. So I had -50 is equal to -135 times 2 plus b. Solve for b, and -50 plus 270 is 220. And then the equation of your line is -135x plus 220. And you can always check these things if you have a graphing capability. -5x to the 4th plus 7x squared minus 3x plus 8. Okay, so there's my function, quartic. I'm interested in the tangent line at 2, so I got to make sure I can see the function value at 2. Okay, that's not bad. And then my line that I came up with was -135x plus 220. Does that look like I actually graphed the tangent line to the function at 2? Yep. Yes, and it's going to have a y-intercept at 220. Yep, so the equation of this line, its y-intercept is 220, so that's where it crosses. So you can check, when you're asked to find the equation of a tangent line, you can check if you've done it correctly by graphing the function, graphing your line, and seeing, is it in fact the line that is tangent to the graph at that point. So you have this paper, and this is like a mathematical paper. It's relatively difficult to read if you're not used to reading this kind of stuff. So I'm going to try to summarize some pieces of it. So the problem that this paper is addressing is how are the two parties, how do they satisfy a dispute, right? How do they come up with a solution when it seems like none exists? So they give this example that they work throughout the whole thing with Ellen and Frank. And Ellen really wants to go to the mountains, I think. And Frank really wants to go to the beach. We're going to go on this vacation together. And like, you can only pick one. So how are we going to do it, right? So it seems like there's no compromise between, unless you can find a mountain on a beach, right? But so what we asked them to do is to each give some sort of ranking to their choices. They give a number to how much they want to do those things. So we have the mountains and the beach, and we have the status quo, which means stay home, right? We're just not going to go anywhere. It was the status quo. So we're just going to assign these numbers and think of them as hearts, right? How much the unit of these units on these numbers are hearts. How much that person would love to do that. Okay, so it's kind of a measure of happiness. If it makes more sense, you could think of it as, say, we're going to measure happiness in dollars and make it all dollars, if that makes more sense to you. Okay, so Ellen is ranking the beach at a 6. 6 hearts for Ellen to go to the beach. And the status quo for Ellen, which would be staying home, right? We don't go on vacation at all. She's going to give that 7 hearts. So she would actually prefer to stay home than to go to the beach. And then, oops, the mountains, Ellen is going to rank that as a 10. 10 hearts to go to the mountains. So you can see this is the order of her preference would be beach, stay home, go to the mountains. She would prefer to stay home than to go to the beach. She would prefer to go to the mountains than to stay home. So those are Ellen's utilities. And then we ask Frank to do this also, completely independently, and we've given them 0 guidance on how to rank these things. We didn't say rank it on a scale from 1 to 10. We didn't say rank it on a scale from 1 to 100. We just said assign some numbers that represents how much you want to do these things. Okay, so Frank comes up with his numbers. He's going to go to the beach. His ranking for the beach is a 10. And his ranking for staying home is a 3. And his ranking for the mountains is a 2. So his order of preference is exactly the opposite of Ellen, right? He would most like to go to the beach. He ranks that at 10 hearts. Then he would stay home, ranks that at 3 hearts. And then he would go to the mountains, 2 hearts. Okay, so because these are like on completely different scales, we cannot compare Ellen's numbers to Frank's numbers, right? It doesn't make any sense because they're not on a common scale. So for example, Ellen could just have easily made her rankings 60, 70, 100. Right? And that would be equivalent to what she has written here. Or she could have made her rankings 5, 6, 9. Right? She could subtract 1 from all of them because these are completely arbitrary numbers. She just made them up, right? So she could double them, she could halve them, she could add or subtract something from them, and it would be equivalent. Okay? They would be equivalent because the ratio of how she feels about the mountains to staying home to how she feels about staying home to going to the beach would be the same, right? So the difference between 10 and 7 is 3, and the difference between 7 and 6 is 1. So she has a 3-to-1 ratio, preferring the mountains over the beach. 3-to-1 ratio, mountains over beach. And if she had ranked her, if she had made her numbers 60, 70, 10, it would still be a 3-to-1 ratio, mountains over the beach. Kind of make sense?
They are the more neutral.
Yeah. Yeah, then there wouldn't be that big of a difference, yeah. Okay, so because we asked them to do this completely randomly with no guidance, we are saying that to determine if Ellen and Frank's utilities are actually equivalent, there has to be some kind of line that links them. Okay, so think of these as points, Ellen and Frank. So later on in the reading, you start making two axes, and the x-axis is Ellen and the y-axis is Frank. So if you were to plot 6, 10, right, Ellen and Frank's utilities that correspond to the beach. Plot 6, 10, and 7, 3, and 10, 2. If all 3 of those points lie on the same line, we say that Ellen and Frank's utilities are equivalent. They feel the same about the mountains and the beach. Is that the case here? No. Those points, 6, 10, 7, 3, and 10, 2, do not lie on the same line. So we can't just say, oh, they have the same feelings. We'll go to the whatever, right, wherever they both agree to go. So these are not the same because those points don't lie on the same line. So some points equivalent to Ellen's 6, 7, and 10, like I said, would be 60, 70, 100. 0, 1, 4 would be equivalent because I subtracted 6 from all of them. So you can multiply by something, you can add or subtract something, And you get an equivalent set of utilities. The U stands for utilities, and they're like the hearts. How many hearts? So that's the utility stuff. So if two utilities lie on the same line, where you plot Ellen comma Frank, they're equivalent. Okay. And it asks you in exercise 1, what are the A and the B? That's the slope and the y-intercept of the line that they lie on. Okay. All right, moving on. Just because I wanted to do a little bit of everything. So that was a little intro to exercise 1. Okay, so in exercise 2, we talk about probabilities. So if we go back to Ellen and Frank's utilities, as a matter of notation or normalizing, we tend to make the status quo utility 0. So you can always add or subtract something from every utility and get an equivalent set of utilities. So for Ellen and Frank, I want to make the status quo 0. So Ellen's new beach utility, oops, and status quo and mountains. Okay, so to make Ellen's status quo utility 0, I would just need to subtract 7. So I'm going to subtract 7 from all of her utilities. So I'm going to get -1, 0, 3 are her new utilities. And those are equivalent to the original utilities I wrote, because 3 minus 0 is still 3, 0 minus -1 is still 1, so the ratio mountains to beach is still 3 to 1. And then we do the same thing for Frank. And those come out to 7, 0, -1. Okay. So imagine that Ellen and Frank have this argument every year. Are we going to go to the beach or are we going to go to the mountains? And every year we have to pick an option. So Ellen likes the mountains so much, she gets 3 hearts of happiness by going to the mountains every time they go to the mountains. And every time they go to the beach, she has a negative heart of happiness. Okay. So if she got to go to the mountains for every 3 times she goes to the beach, she ends up neutral, right? So because she gets so much happiness from the mountains, she would say, okay, I'll go to the mountains once for every 3 times we go to the beach, because she gets that big of a payoff from going to the mountains. And it might make more sense if you think of happiness in dollars. Like if she gets $3 every time she goes to the mountains, she loses $1 every time she goes to the beach, then as long as she goes to the mountains once for every 3 times she goes to the beach, she breaks even. Okay, so it's the same thing with hearts or with dollars. Okay. So we set up a lottery where Ellen would be perfectly happy if we set up a lottery where 2/3 of the time we go to the mountains and 1/3 of the time we go to the beach, right? Because that would give her a sort of a neutral outcome of the status quo. 2/3. No, I think it's. Oh yeah, sorry. 1/3 mountains, 2/3 beach. Yeah, she'd be happy with that. 1/3 mountains, 2/3 beach. Okay, so exercise 2 says find the coordinates of the points corresponding to the following lotteries. Okay, so we can plot these utilities. Ellen, Frank, right? So for the beach, we have -1, 7. So that's like right here. Beach. -1 is Ellen's utility for the beach, and 7 is Frank's. Status quo is at 0, 0. And the mountains is at 3, -1. The mountains. So there's our, this is called the payoff polygon when you connect these. Payoff polygon. So when you assign a lottery to the different utilities, to the different outcomes, we get some point on the polygon. So for 2A, lottery 1, we're assigning the status quo a probability of 1/3 and the mountains a probability of 2/3. So we're not saying this is the fairest thing to do in any way, right? We're just saying that just for practice, if we want to figure out the most fair lottery that would make them both happy, first we just have to know what that means to do a lottery. Okay. So the status quo is 1/3, the mountains is 2/3. So for Ellen, we multiply her status quo score times 1/3 plus her mountain score times 2/3. Right, so we're giving 1/3 of a chance for the status quo, 2/3 of a chance for the mountains. Multiply those by her utilities, and you end up with 2 hearts. Right. So if we used this lottery, Ellen would love it 2 hearts. Right. Okay, and Frank, if we use this same lottery, assign 1/3 to his status quo, 1/3 times 0 plus 2/3 times his mountain score, which is -1. Frank loves this -2/3. He has -2/3 hearts of love for this lottery. So he's not particularly happy with this, right? And then we can plot that point to -2/3. I didn't put things on here, so I don't know exactly where it is. Right about there? In the payoff polygon. Okay. So that is the point that corresponds to lottery 1. And I was going to talk about the supplemental exercise, but I ran out of time. So Friday, we're going to have a class dedicated to the projects. I'll talk about it a little bit more then.